at the outline of the course and perhaps review it very briefly and give some motivation for being interested in finite sample theory. Of course, econometricians for the last 10 years have mainly, and before that, have mainly been discussing asymptotic theory of their various estimators. Only gradually, since about 1958, has some attempt at finite sample theory been made. And perhaps the main reason for this delay is that I think most people have thought that asymptotic theory was rather a good approximation, that it worked rather well. And in fact, to go back to the early days, in the early simulation studies, such as those done by Summer in the late 50s, or by many people since, it did look as though the numerical calculations of the properties of exact finite samples for simple models seem to validate asymptotic theory in the sense that the minimum sample size, T, capital T I shall always be using for sample size, such that the cumulative distribution function is within delta of the asymptotic cumulative distribution function, was clearly model dependent, but appeared for a wide range of models to give pretty good accuracy. That in fact the minimum sample size required for an accuracy within 1% was in the range of 20 to 50, which is of most interest to econometricians. Bob Summers' early work, for example, in simulating simple models, and work, for example, done by Mikhail at LSE, published in JASA 1971, seem to carry the same message. These all based upon Monte Carlo simulations. Of course, the limitations of this work were that it was concerned with rather small models, only 2 or 3 equations, perhaps up to 4 exogenous variables. But I think the main limitation was that the models were static, did not have any lag-dependent variables in them, that they had non-stochastic exogenous variables, what I would call a classical static model, and also, of course, that they used normally distributed errors. And all the exact finite sample theory that's been developed throughout most of this period has actually made the same set of assumptions. Now, clearly, if within these limitations one studies a model which is almost non-identified, then you're likely to get rather poor approximations through using asymptotic theory. And it's clear that the adequacy of the asymptotic theory is very much related to the degree to which the model or the equation being studied is identified. But another feature which has arisen as soon as people have started to look at simple dynamic models is that there the asymptotic approximations may be much worse for a given model size. Just to write down the model which I shall be using to some extent, and I have used in the past to a large extent, to look at the adequacy of various approximations. Let's start with a simple model, which is the obvious generalization of the simple model that Peter Phillips looked at in his 1980 paper. which he simply looked at the simple autoregressive model, which the UT is the usual written as a vector normally distributed with mean, zero, variance matrix, sigma squared times I. And the obvious approximation, the obvious generalization of that is to introduce a set of non-stochastic exogenous variables so the xt are a vector of k times 1 non-stochastic exogenous variables. Beta is a corresponding k times 1 vector of coefficients. One studies the properties of this when estimated by OLS. So if we denote the OLS estimators as alpha prime, as alpha hat, beta hat, then one can work out something about the probability densities for the alpha hat and the beta hat, the exact finite sample distributions. But it's also a good model, a simple model, to study the properties of various approximations to these finite sample distributions. In fact, one can obtain the exact finite sample distributions in this simple kind of model by using the Imhoff procedure, Imhoff, or various alternative numerical computation methods. But I stress Imhoff because I'm going to talk quite a bit about Imhoff in the subsequent lectures, and I'm going to lead off in my next lecture by looking at the use of this kind of procedure for studying von Neumann ratios, Durbin-Watson statistics, and various other things of this sort. But this has the great advantage that if one wants to then compare the performance of different methods of approximation of the finite sample distributions, one can actually compute the exact finite sample distributions, which is in fact not possible in the majority of cases where one is looking at these Edgeworth and other approximations for a wider class of statistics. So I think even at this stage I'll go a little further in developing the algebra of this particular model. Clearly the finite sample distributions depend upon everything we've specified here, that is upon the true alpha, beta and sigma, and also upon the actual xt. When one looks at the asymptotic distribution compared with the finite sample distribution, one finds that the critical things appear to be the values of alpha and sigma squared, and perhaps I might discuss very briefly here why that is the case. Alpha, of course, in the simple autoregressive model is the only parameter of interest, and there what one finds, as one might expect, is that alpha is of course normally taken to be less than 1. As you take values of alpha closer to 1, even as close as 0.7, the asymptotic approximation becomes rather poor. If one studies the extended model with the exogenous variables, one finds that usually for a given alpha the approximation is rather better, because one is in effect introducing a set of exogenous variables into the problem, and the asymptotic approximation, of course, is one in which one treats the variables, the right-hand side variables, as though they were all exogenous, and one would expect that if one introduces further truly exogenous variables, then one would improve the approximation. The obvious way of discussing the matter is to split up the yt into a systematic part and a random part, wt being defined to satisfy or in other words, to be given by a formula of the form this, of course, is assuming stationarity, the usual kind of way, and with the same kind of summation formula for the explicit formula for the Vt. Now, the important criterion, I think, for the value of sigma squared is really something of a ratio type criterion. One wants to think about how important these terms that I have in the bracket here are compared with the ut minus s, which will in turn determine how important wt is compared with vt. And this is rather a heuristic way of putting it, but what one might consider doing is to work out in effect, the second moment of the variable in the bracket here, the beta primed xt that's occurring there, and compare it with the second moment of the ut, which of course is just the sigma squared. And if that ratio is large, in effect, most of the yt is, if you like, determined by the wt. The vt is relatively less important, and so you can think of the yt as being mainly non-stochastic, and therefore you'd expect that you could treat yt minus 1 here as though it were non-stochastic. And since, as I said before, the asymptotic approximation is very much the distribution you would have if the yt minus 1 were non-stochastic, you can see that if this ratio is large, then you'd expect the asymptotic approximation to be rather good. And on the contrary, if the ratio is small, then you'd expect that the asymptotic approximation is rather poor. So that's one of the main determinants of the adequacy of the asymptotic approximation. We have then just the two, this ratio, and how close alpha is to 1. And indeed, when I and Say did a study of the Edgeworth approximations to the distributions of the alpha, beta, OLS estimates, the alpha hat and beta hat, and as part of what we were doing, compared the asymptotic distribution with the exact finite sample distribution computed using HIMOF, we did find that we got some rather poor approximations. I'll just quote a few of them. You can, of course, alternatively, in place of this kind of approximation, use the multiple correlation estimated in the usual way. That is the not the adjusted one, the raw multiple correlation, because again the multiple correlation will be large when sigma is small compared with the variance of the x's. Just to quote a few results, when alpha is 0.8, sigma squared relatively small, corresponding to a capital R squared of about 0.95, we find that the and the sample size, by the way, is 20. All my sample sizes I'm quoting here are for sample size 20. We find that the true finite sample proportion outside the 95% asymptotic confidence limits, in other words, we're taking the 95% asymptotic confidence limit for alpha hat I should say, is 12% roughly, varying slightly with the way that we generated the xt's. The same kind of alpha with a large sigma, that is with r squared about 0.6, we had a proportion of 22% outside. On the other hand, if we brought alpha down to 0.5, so it's kind of our standard case, then these came down to roughly 7% and 10% respectively. In other words, if both alpha is in the region of 0.5 and the equation has let's say, a good fit, then the 5% confidence interval is not too bad an approximation. But clearly, if you are going to consider cases where the proportion outside your confidence intervals are twice what can be expected, what the asymptotic theory predicts, then one is getting rather poor results. One is making tests which are not very valid. So, what can one do to develop finite sample distributions? Well, perhaps at this stage I can make a distinction which seems to me to naturally arise from my discussion of what happens with sigma when sigma is small, and talk briefly about small sigma asymptotics. One's familiar with the idea, and this is precisely what the case is here, that if we consider the limit distribution as sigma goes to 0, rather than as t goes to infinity, one is dealing with small sigma asymptotics. This is an example of a case where, in fact, the two cases give you the same asymptotic distribution, as I shall point out later, but this doesn't necessarily occur always. And one method, which I think is in most cases the only practical method for models that one is really interested in estimating, is to use an expansion approach. In effect, taking the asymptotic distribution as the first in a series of approximations to the finite sample distribution. And just to introduce my general notation in this field, I will usually be interested in some function xt, which is, if you like, xt of some set of data. I shall simply call it S for the sample. Now the sample, of course, is also going to be of size t, so perhaps we temporarily put a suffix t on there, and xt is just defined as some function of the sample observations, which of course will generally depend upon xt will not depend upon the actual parameters of the model necessarily, but of course in some cases it may. Very frequently we will be taking the case where x is a function of st, which is independent of t and is independent of theta at least. Well, so xt is just a stochastic variable depending upon a given set of data, and if we use mu t to be the expectation of xt, then very often, in order to get something which has got an asymptotic distribution, we'll take the difference between xt mu t, multiply it by square root of t, and find that we have something which has an asymptotic distribution. So then we can consider the probability that xt less than or equal to r in the usual way to give us a cumulative distribution function ft of r. Well, that's a little unfortunate, my notation, because I'm immediately going to contradict it. So instead of doing that, let's simply write that it may be possible to find an expansion, which I'll label 1 for the time being, well, and we're interested in the case where the f's do not depend upon t, and the result is that we have a series of terms in our sum which are all of relative order t to the half, t to the minus a half compared with the previous one, each of us giving a closer approximation to the exact finite sample distribution. You might say, well, why not let it run to infinity and consider whether for each r there is such a convergent infinite series for the distribution function. I'll come back to this question as to whether you can rely upon this sort of thing to converge later, but just for the moment let's consider the possibility of such an expansion. That kind of approximation I'll call large T asymptotic, and I've already mentioned Edgeworth expansions, but there are various expansions of this sort, and I'm going to look at 2 or 3 in the course of these lectures, depending upon how far you regard my different expansions as being, in fact, separate cases. The alternative is to consider an expansion of this sort Now, in this expansion, FJR clearly depends upon sigma. The actual distribution function clearly depends upon sigma. And in this expansion, the FJR, I'm sorry, this should have been, I'm very sorry, I've made 2 bloomers in presenting these infinite expansions. It's the t to the half should be a power to the power j, and sigma to the power j in each expansion. This is intended to be a j, not a 1. In fact, it's often found that the first term in these expansions are the same, that f0 star r is the same as f0 r. And that can usually be shown to be a general property of models, depend upon the general property of models, which I won't discuss at the moment. But very often the later terms are different. And people have raised the problem of which is the most interesting of these expansions. To me, it very often seems that an expansion which is only good when sigma is relatively small is an expansion where that is not too interesting, because very frequently in that case the asymptotic distribution is really quite a good approximation, and that on the other hand it's frequently the case that we are interested in the range of values of t, fairly large values of t, where the first expansion is most interesting, where the expansion is still valid if sigma is relatively large. And so I shall only be considering case 1 in these lectures. Case 2 is in the literature, and notably Ted Anderson has done work on this kind of expansion for the small sigma asymptotic type of expansion, but not many other people in the field. Well, let's have a look at how we can study finite sample properties. The earliest method, which I've mentioned already, is by using simulation Monte Carlo studies. The advantages of this, of course, are that it's once you have computer time, then it's relatively easy to set up the study. It is there is rather a tendency, because despite the fact that computers are free goods in England at least, but perhaps not in the rest of the world, there is in fact a good deal of organization required in order to obtain any kind of general results. Because there is in effect a kind of computer budget constraint on most of these estimations, it does tend to lead to concentration on simple small models, and even if one makes use of the kind of tricks of control variates and various other types of methods of improving the efficiency of estimation, or rather, yes, it's essentially a problem of estimation from the generation of artificial samples. It's usually found that people are, in effect, not able to study a very wide range of cases. Given this, it's then a little difficult to achieve generality, despite the work by David Hendry and others on using response surface methodology, which is basically an attempt to estimate a regression of the various moments of the estimators or test criteria that are being simulated across model characteristics. Theoretically, what one needs to do, one can do, is to take relatively small Monte Carlo samples for each type of model and then run a regression across the results for such small samples for different models. But the problem with this is that it's true that the actual relationships are extremely complicated. What determines the bias or the second moment or the third moment or the fourth moment of a given estimator is a very complicated function of all the parameters of the model. If you have a very large number of parameters, as you do in any realistic model, then it's very difficult to specify a simple response surface, a simple regression equation, which is adequate to explain this variation. Now, I'm not myself quite as strongly against Monte Carlo simulation as Peter Phillips, but I do think there is something in this statement that it is difficult to explain what is happening very well. And one can see this by looking at how much of the variation that is being obtained would be expected. Now that's a little difficult when one is working with such things as second moments. But one can look at it, for example, when using a straightforward simulation technique for estimating the probability of being outside a given confidence interval. This is something one very often needs to do in this field when one is checking on the adequacy of various approximations to distribution functions. Essentially what one can do in order to see whether one is approximating well the exact finite sample distribution is to use a large Monte Carlo simulation with up to 10,000 replications of the model, of the estimation procedure, and then compare the observed sample proportion outside a given confidence interval with what is expected from the approximation, the Edgeworth expansion, or the small sigma expansion. And what one can then do is use the binomial theorem to see what the distribution, how much of the observed variability in one's regression is simply due to sampling, straightforward to sampling error. How much of it is due to the regression equation that one is using, not in fact being the true explanation of the probability. And what one usually finds, in my experience, I've done some of this checking, is that only about 50% is true sampling error, and the remainder is misspecification of the form of the regression equation, the response surface regression equation across the models. So that makes it fairly clear that crude regression equations of this sort give you some idea of the effect of varying, say, one parameter on the property of the estimator that is being estimated from the regression equation. But that it is not a very good way of doing anything except give a crude summary of the effect of the model's characteristics on the distribution of the estimator. Of course, on the other hand, it does give one, even in quite complicated cases, some check on the adequacy of these approximation procedures. Well, the second approach I want to discuss is exact theory, that is to actually analytically work out the form of the distribution functions. This is, in fact, very difficult to do, even for relatively simple econometric models, even for relatively simple econometric estimators. One method which I'm going to discuss at some length, and I've already mentioned, is a method which involves using the characteristic function of the estimator or the test statistic. If one can get an analytic form for this, then one may not be able to obtain a corresponding analytic form for the distribution function, but one can use a numerical integration using the computer to give an approximation to the actual distribution function. Merely an approximation because one has to truncate the integration of the characteristic function. One can't go to infinity in a numerical integration. One has to therefore take a range which is large but finite. And then, of course, one is going to use some kind of numerical approximation which is only as good as some kind of Taylor series expansion for small intervals which are used to define sums. Nevertheless, it's clear that this will often give a very good approximation, and that it's not too difficult to check on the errors in the approximation caused in these ways. Well, there are two problems with this. One is that since one is doing it for a particular model, it has almost the same kind of problem as Monte Carlo, that you can only look at a finite number of models, and if you've got a model which depends upon a large number of parameters, then one can't explore the sample space at all easily, or rather the model parameter space at all easily. Then the other thing is that it has been used only where the characteristic function has a known form, and though this covers some types of elementary models that we're interested in, it doesn't cover very many. Now, for example, in this model that I've looked at here already, you can use this kind of procedure for the distribution of the alpha hat, the beta hat, but if you're interested in, for example, the t ratios for the alpha hat and the beta hat being significantly different from 0, or you're interested in the Durbin-Watson statistic for the UT, or something of this sort, none of these can be treated in this way. So it's a relatively limited field. Then Of course, one has the work that's been done to develop expressions for the probability density for simple estimators, for simple models of a simultaneous equation type. Now, the simple cases that are involved are those where you are estimating an equation by single equation estimation procedures, like two-stage least squares, limited information maximum likelihood, instrumental variables. But the equation contains only two endogenous variables, one of which is standardized, has a standardized coefficient. There has been quite a lot of work done on this since the early 60s, and I shall be reviewing some of it in this lecture course. Even so, you find that the actual expression for the probability density involves doubly infinite sums, infinite series of sums, where one has to sum over two suffixes, that these converge rather badly, so that the higher order terms in these sums are important. In other words, one can't truncate the infinite series easily at low values. And then what one is usually interested in doing in order to make comparisons is to actually compare the cumulative distribution functions rather than the densities, so that one has to work out the densities for consecutive values of the coefficients, and then do some kind of numerical integration to get the CDF. Well, this has been done by Anderson and his co-workers, and to some extent similar procedures which involve working with integrals rather than infinite sums by myself and Mikhail. But again, what one finds is that in order to explore what happens for different models, you simply have to work these things out for a large number of different models. It is still not possible from these analytic expressions to have any kind of simple notion of the effect of varying the parameters of the model. The effect of the set of parameters on the CDF is quite opaque. You can only do the same kind of thing as you do for Monte Carlo studies, work the thing out for various cases, and then perhaps do some kind of response surface regression. The situation is much worse still when you consider more general cases where the number of endogenous variables is greater than 2. For one thing, the theory is much more difficult. It gets into the realms where relatively few people understand it, and the expressions for the densities require infinite summations over in higher dimensions, with larger number of suffixes being summed over. Each term in such a summation involves polynomials of a specified form, the so-called zonal polynomials. The coefficients of the zonal polynomials are defined for given degrees of the polynomials, but these coefficients have not been worked out up to higher than about degree 20 at the moment, though there are computer programs which are going to be set up which will do higher order things. But in fact, you have to use multivariate zonal polynomials, and there hasn't very much work been done on these yet. The simple one-dimensional zonal polynomials are being worked on quite well. The effect of that again is that very little, in fact I think Peter Phillips is about to do some actual work on the distribution, for example, of a two-stage least squares or instrumental variable estimator for these models, but his present papers contain the formulae, but the actual programs for computing these formulae have really not been operated yet. You can alternatively approach these things by using multivariate integrals rather than multivariate summations, infinite summations. And there, of course, it's a question of doing numerical integration in several dimensions. The number of dimensions, again, goes up very rapidly with the number of endogenous variables in the equation being estimated. So it seems to me that although this theory is going to be developed rather rapidly in the next few years, it's going to be some time before we find really useful results for models of the size which most econometricians are working with. So I come to back again to my discussion of asymptotic expansions, and this, I think, is the method which is most likely to produce results within a short period of time. In the next 2 or 3 years, I would expect things might be developed to a stage at which we can make some use of these expansions to improve our asymptotic distributions. And in order to understand what the problems are here, one has to understand that these expansions that I gave, which are still on the board here, can't be taken to run to infinity, because we find that in general the infinite series that we might theoretically specify here do not converge, so that we have instead to consider what happens when we truncate such a summation at a given series of terms. What I can do is simply to change the summation so that it runs up to a finite number s, and then add a remainder term. I'll call it rs and r star s, just to have a simple notation. In each case, what we're claiming, you see, is that this expansion is good if either t is sufficiently large in the first case or sigma is sufficiently small in the second case. So what is our criterion of whether the first s terms, or s plus 1 terms, in these expansions is a valid asymptotic expansion? Well, there are usually two things which can be proved: a weak kind of validity and a strong kind of validity. The weak validity is to look at Rs and say that that remainder is of lower order of magnitude than the last term in the expansion. Now, formally, we write that in the form that Rs is of order, in the first case, little order t to the half j. Sorry, t to the minus half j. And that simply means that we're requiring that t to the half s. T to the half s times Rs limit as t goes to infinity is 0. So that's just the usual idea of an order of magnitude, and in effect it says that by taking t sufficiently large, you can ensure that the remainder is relatively small compared with the last term that you're retaining. Of course, it's not saying how large t has got to be before that occurs. The same way, you, in the second case here, case 2, you would be interested in, as a weak validity requirement, that Rs is of order sigma to the half s. And the same idea as to what is involved. Now, this is the weak validity. The strong validity would change this, and it's convenient actually for me to do it on the blackboard, so let me now do it on the blackboard. Strong requires that it be of order half s plus 1, and the same here, that the requirement is that Rs is of large O, half s plus 1. Well, again, to remind you what orders of magnitude here mean, what we're then saying, taking this case, is that if we take Rs multiplied by t to the half s plus 1, that this is bounded as t goes to infinity, and the same here, that if we take Rs divided by sigma to the half s plus 1, that is bounded as sigma goes to 0. Now, these kind of criteria are well known in pure mathematics, and they're denoted by using the word asymptotic in a way which is different from the way it's used in statistics, because it's quite without any stochastic connotation. And if we thought of these as being just a series of functions, and that fr here depends upon t, and we're considering the behavior of this expansion as t goes to infinity, and we have this kind of property, this strong property, without the f's necessarily being anything to do with cumulative distribution functions, but with f as a general function of r and t, then it would be said that this sum was simply an asymptotic sum or an asymptotic series. So instead of talking about convergent infinite sums, one talks about convergent infinite series, and one also has a kind of special notation which again is unfortunately overlapping with notations used in statistics. People use the tilde to say that FRT has a valid asymptotic series or sum, and this is given by some set of formulae of this kind, where the essential property that makes it a valid asymptotic series or asymptotic sum is that the remainder, if you like, the error in the approximation, is of the same order of magnitude as the last term in the series. Is of the same order of magnitude as the next term in the series, the one that has been omitted from the series. Well, I've overlapped. Sorry, no, I go into 11, don't I?
Well,
yes, sure. I've got plenty of stuff here to go into 11.
Well, should we stop here?
Yes. Okay.
We can make it 12 hours rather than, if we go for an hour and a half for the first 2 days of each week, it would make it 14 or 15 hours.
Well, I really have. I was thinking in my usual hourly lecture context, but I really had prepared a little bit more to say.
Yeah.
The question of whether.
Put another time if you want to have a break.
Should we have a break and questions? Should we take a few questions then?
Sure.
Yeah.
While you change the day.
Yeah. Sure. So.
Okay, we'll take questions while you change the tape.
Yeah, that's it.
Right.
I hope we have some questions.
What, you want me to stop here?
Yes.
I think
Yes.
so.
Yes. Yes. Using Taylor series expansions, in which we're thinking of the xt as depending upon being functions of a set of, in fact, sufficient statistics. These are in practice the second moments of the data, so that the PT would typically be the second moments of the data, and these are, of course, what our estimators depend on when we have models which are linear in our variables, though not necessarily linear in our parameters. So I will often be considering this kind of case where we have a given estimator which depends upon the second moments of the sample data. Now, it has not been shown, but except in very recent work by Jim Durbin or by myself and Steve Satchell, that such second moments have themselves got Edgeworth distributions. But if we can assume that the PT have Edgeworth distributions in the kind of models that we're interested in, then we consider a transformation from the xt to the pt using the f function as the transformation, and we approximate the f function by using a Taylor series expansion about the expected value of pt. And through a rather complicated series of arguments, which I shall mainly not discuss very much, one can derive Edgeworth distributions for the xt by knowing the Edgeworth distributions of the pt. And these Edgeworth distributions are closely related to normal distributions and can usually be written in terms of finite expansions, of the derivatives of normal distributions. The coefficients of these expansions are in fact quite complicated to determine, but have the advantage that they can be determined for any kind of model and for almost any kind of estimator, provided that enough derivatives of the f functions are finite, existent or are finite or bounded within the regions surrounding the expected value of pt. So that's the first kind of expansion. The second kind of expansion is the so-called saddle point expansion. Again, Jim Durbin, in his recent article in Biometric in 1980, has discussed these saddle point expansions in relationship to time series models in a way which is very innovative and very relevant to most econometric estimation. And I shall give a fairly elementary exposition of some of his results. Finally, to go back to the expansions which were really the starting point of finite sample theory applied to econometric estimator, the Nagar expansions which he first wrote about in his 1958 Econometric article. There the basic idea is that one starts with an expansion for the estimator itself, I don't suppose this comes out too well on the screen. Which we can write x star Now again, the basic idea is that we want to now take a stochastic variable xt, expand it in the same kind of form as we did for the distribution function, but of course each of the xit's is going to be a stochastic variable depending upon the observed sample data, and we're going to have a remainder on this expansion rst, and we can very frequently make such an expansion which has the property that RST is some appropriate stochastic order of magnitude, either for a weak validity that it's order t to the little order t to the half s, t to the minus half s, or that for strong validity, so this is weak, this is strong, same kind of idea as before. Well, so we're probably interested in some moment of xt, say that we're interested in the kth moment. We introduce the notation mu k t is expectation x t to the power k. Well, it seems plausible that you might be able to write that in the form expectation x star st to the power k plus a remainder RK ST. And that is the Nagar approximation, fundamentally, that one takes the Now, in order, of course, for this to work, one needs that all these expectations exist, which means that you need that X star ST has, and so each XIT has kth order moment. And a clear contradiction was realized early on, that in some cases at least, you have a proof that the kth moment of xt doesn't exist, so that this expectation is, if you like, infinite, and yet each of these terms in the summation that results from substituting what x star st is as a summation into here have finite moments. So it's clear that such an approximation is not always valid, and so first of all one requires some discussion of validity here, but the kind of property that we look for again is that the RK ST, I did this form, is either, on the weak assumption of order t to the minus a half s, or that it's of order t to the minus half s plus 1. And one can prove in practice that this kind of condition will be satisfied for the type of models that we study, particularly in the simple static, classical static model. This kind of thing is relatively easy to prove. With a kind of very general assumption which either involves that the moment that's being approximated is itself finite, provided the moment itself is finite over a wide range of models, or alternatively that some higher order moment is finite will often do. This is the kind of thing that I myself discuss in my 1974 Wallace-Bowley lecture, published in Econometric in 1976. Now, again, I don't know that I shall be discussing this validity argument very much, but I will be giving some illustrations of the use of the method and stating some results on validity. And that, I think, actually brings me to the end of my course outline and the end of this lecture. So let us finish with a few questions. Are there any questions?
I have one question about this last,
Yeah.
another one.
Yeah.
Well, usually, in most applications, the xt would be the ratio of two functions. Even if you assume normality, usually the moments of xt would not exist. Or do we have applications that actually exist?
Oh, yes. Well, take the case that you're interested in the moments of two-state least squares estimators. You first of all have the just identified case, and there indeed you're right in saying that none of the moments exist. But then if you look at the over-identified cases, what you've got is a ratio. You can certainly express it as a rational function in which the denominator is a determinant, and the determinant is that of a second order matrix which will only have a zero value with a probability which is relatively low. Let me actually write down a little bit of algebra at this stage. If you look at any particular estimator, well, I actually like to write this kind of thing in the kind of form that you've got an x prime z, z prime z inverse, z prime x times beta hat equals x prime z, z prime z inverse z prime y. And after some struggle, you can take any particular element, say the ith element in beta hat, and find that you can write it as a ratio of two polynomials, and the bottom polynomial is in fact just the determined x prime z upon t, z prime z upon t inverse, z prime x upon t, that sort of thing. Now, x, I better define my variables a little bit more for those who don't know my notation. X are the actual equation we're estimating is yx beta plus u. Then we have a set of variables, instrumental variables z, and we're using these to estimate the beta, and we find that we get this kind of equation here. So the x prime z are in the just identified case, the x prime z is a square matrix in general non-singular, and you can do a lot of cancellation out of a formula like this, and instead of having this kind of determinant, you simply find yourself with determinant z prime x upon t. On the other hand, if the model is over-identified, then you find that x prime z is rectangular, and in effect, if this is going to be singular, then you have to have the x prime z satisfying more than one constraint. You can think of it being singular because you have some annihilator which applied to it makes it zero, and that annihilator is of dimension greater than 1. That has the effect that in order, if you look at the probability of this being small, it is such that the moment of beta at I of the first order at least exists. To get to second order, then you have to have a higher degree of over-identification. But in other words, it does depend very much upon what the form of the rational function is, and the denominator of the rational function may only be zero with a probability which makes the or near zero with a probability which makes the moment still exist. Quite a problem, however, to sort out what is happening here, because whenever the determinant here is tending towards zero, you find also that the numerator is also tending towards zero, because it contains x prime z's which are tending to singularity in the same way that the determinant is tending. So the x prime z's are tending to be not a full rank in the same way that the x prime z's below are tending to make the determinant 0. I didn't say that I was going to look at the existence of moments, by the way, but that is a kind of separate subject entirely, and I thought I was going to keep away from that, so I haven't got my thoughts very well prepared on that.
How sensitive are these approximation to the normality assumption in the disturbance term?
Well, they are very sensitive. However, you can still tackle the problem of non-normality, because it is still true that even if the errors are non-normal, then the PT that we've got in this expansion that we use in the Edgeworth approximation may still have an Edgeworth distribution in the same way that the PT is asymptotically normally distributed. It will still have an Edgeworth distribution itself, and all that's going to happen is that the Edgeworth distribution of the PT is related, and the coefficients in the Edgeworth distribution functions are related to the cumulants of the PT, so that if you can work out what the cumulants of the PT are, given that the U's and the V's in the models are non-normal, then you can still use the Edgeworth approximations, so that the Edgeworth approximations can still be worked out for non-normal cases. But of course, the distributions, the finite sample distributions on the Edgeworth approximations will depend upon the degree of non-normality. However, since we often specify non-normality simply in terms of the moments, the fourth moments and or fifth moments, sixth moments, whatever moments you like, being not those of the normal distribution, so if we're prepared to do that, then we can in fact work out relatively easily what the change is in the Edgeworth approximation to the distribution of the PT, and so the final distributions of the estimators we're interested in. Okay.
If you had finite elements up to the order of over-identification, suppose you are going to care over-identifying restrictions. So, all right, you have finite moments up to order.